Okay. Cable. All right. I'm so happy to see you guys without the masks. It is optional. So if you need it, I fully respect, and I think that's very safe as well. So no pressure, okay? All right, this is the screen. Okay, good deal. Okay, so shear. All right, every time I begin the class, I always ask, what is concrete good for? What is concrete good for? Compression. What is steel good for? Right. So in terms of shear, is concrete good for shear? Remember the boring video last time about Wu's old tactics, cliche, boring. What we learned, is concrete good for shear? No, horrible. Okay, and wake up. All right, steel is good for shear. All right, reinforcement is good for shear. But steel, right? In shear, there are two components we learned from last time: the concrete and the steel. Right now, the concrete resistance in terms of shear have three components. Is that right? So starting from the first thing, right? Pull out your lecture notes, right? And we said, if I draw the free diagram of a beam from last time, a complicated stress drawing, and nobody knows what's going on, right? And if you feel like that, you better go back and review the mechanics of materials, right? Find out the definition of principal stresses and try to understand the trajectory of how stress distribute in the beam. But we said last time, if I do a free body diagram, specifically along the diagonal shear crack, and there's nothing outside the window, sir. There's nothing outside the window, sir. The main show is here, okay? You bought the ticket, please don't waste it, okay? Now, here is my free body diagram, right? Free body diagram. And now I have a reaction force, of course, from the support, all right? And then I have a compression force on the top. We know that. So whenever, remember this, whenever there's compression, there will be shear, all right? Why is that for concrete? Why is that? Because compression will cause the aggregate to do what? To do interlock. Is that right? Interlock, and that generates shear. So we will have shear components here. We call it VCY. VCY, meaning the shear resistance from the compressive zone of the concrete. In addition to that, we'll also have shear resistance along this diagonal crack, and we call that the main shear resistance of VA. VA. Okay, and last but not least, right? You think about it, when we have beam, we always have to have flexural reinforcement, or we call it longitudinal reinforcement. That means we have a so-called Dow reaction, Dow action. So Dow action. Okay, that is VD. So these three components consist or compose of the total shear resistance VC that equal to VA plus VCY and plus VD. Right? Multiple choice problem exam number 2, right? What are the main components of shear resistance? A, shear force in the compressive zone. B, shear resistance from the aggregate interlock along the diagonal crack. C, shear resistance from the flexural reinforcement. D, all of above. Which one? All of above. Okay, all of them. All right, so that's about the shear resistance. So now we know what about shear resistance in a concrete, but for design, we need to use the criterion of strength design criterion. So let's recall what we used in terms of flexure design. What is equation for flexure design? That involved the parameter called phi, right? So I start right, try to fill the blank for me. Phi, what? In terms of flexure, phi what? Phi what? And what? And, right? And there's got to be a sign, right? Inequality sign or equality sign. What is this? Greater than or equal to what? And what? U, exactly. That was the design criterion for flexure, isn't it? So on the left-hand side, we have phi, what is called the strength reduction factor. Is that right? Strength reduction factor. We have Mn, is called the nominal flexure resistance. Okay, or you can call it nominal flexure capacity, whatever, right? Nominal is the key word, okay? And this whole thing multiplied together is called design strength. On the right-hand side, ladies and gentlemen, we call it applied load, or sometimes we also call it factored load. And when we talk about factored, what factors we use? For dead loads, we use what? 1.2. Live load, 1.6. And one more thing I haven't introduced, we will, for sustaining live load, we use 1.4. Okay, we'll talk about them later. Okay, but that's what we learned so far. So for shear, dare I say, I will follow the same format. So can I put this way? Phi Vn greater than or equal to Bu. Is that a fair statement to you? Is that right? Right? That's pretty fair, right? We use the same procedure anyway. The only difference is that now phi multiplied Vn has two components. One is what we call Vc, that is the resistance provided by the concrete, and then we have Vs, resistance provided from the steel. And you can find this equation from ACI 22.5.1.1. Right? ACI 22.5.1.1. That is how we design for shear. And this, ladies and gentlemen, remember when we design for flexure, the strength reduction factor phi for flexure equal to what? What is phi for bending, for moment? What is it? The quick answer would be, it depends, right? It depends. Depends on what? Phi depends on what? Epsilon what? Come on, guys, epsilon t, is that right? Right. So remember the nice little drawing here, phi versus epsilon t. When epsilon t is smaller than 0.02, what I got? Come on, 0. What? Got to remember this, okay? 0.65. Go up by 0.005. And by the way, this is called what? Tension control, right? And what I have here, 0.9, right? And then in between linear interpolation, the slope of that is something minus 0.002 multiplied 250 over 3. Is that right? That's how we remember that equation, okay? So Bob, we tested this before. Yes, in the final exam, it's going to be accumulative, right? I will make sure this stuff will show up again in the final. So do remember that. You say, how mean you are? Well, when you go to the job site, they are so mean like this, maybe meaner than me, okay? So gotta remember how to do all this, okay? Gotta remember how to do all this. All right, so that's easy, right? But for shear, phi is no longer a variable. For shear, phi is 0.75 constant. Okay, this is very important. Okay, 0.75 constant. Okay, so no matter what time strain I have for shear, no matter what kind of reinforcement I have in the section, no matter what kind of concrete compressive strength, it is always 0.75. Okay, 0.75. Now, one thing I want to put a notice here: why phi is so low? Instead of 0.9, I have 0.75. What is the reason for that? Now, you got to figure the definition phi is called strength reduction factor, right? Strength reduction comes from two sides of it: the importance of member and the types of failure. All right, types of failure. So for brittle failure, we use lower phi or higher phi. Lower phi or higher phi. Okay, let me turn it the other way. Lower phi, right? And why lower phi? Lower phi, more MN, more VN, more design, more material, more expensive. All right, safer. All right, so shear is brittle or ductile. Remember my odd drawing, ugly video, right? Is it brittle or ductile? Is it take 100 years for those bricks to fall down? No, right? Flash of seconds, right? That means it's brittle, isn't it? So use what? Lower number, so safer. So in this regard, quick question here: is shear more dangerous or flexure failure more dangerous? Shear. All right, very important. You go to the job site, right, and see, the beam is going to fail in bending. Somebody says, oh, the beam is going to fail in shear. You say Bill's beam is going to fail Benny. It's like, get out of here, right? We have a lot of reinforcement. That shouldn't be a big deal, right? But if they say the beam's most likely going to fail in shear, be careful, right? Be careful. That's big no-no. Okay. Matter of fact, most of the beam failure are in shear, not in any way flexure. Have you seen the Florida Bridge? Florida Bridge collapsed down. What happened there? They disturbed the support, right? It failed as support. I-35, there's a rivet, right? Failure. And the crack in the middle, shear as well, shear as well, okay? So that's why shear is so important, so critical, okay? Now we know. All right, so that's fine, right? Keep continuing, then VS then is the reinforcement resistance, right? And then VS has to equal to what? From this equation, fellows, VS equal to what? VU, or VS has to be greater or equal VU divided by phi minus VC. So why I write this equation down? It is because if I know the concrete resistance, VC, okay, if I know that, and I know how much shear force I will apply to the beam, I can estimate how much reinforcement I put into the section. Is that right? So that is our design strategy here. So the question is now, folks, what is VC? They say, Bob, you said VC is VCY plus VD plus VA. We all know that, right? But equations, right? What is VC? What is VC? So turned out the folks at ACI have done thousands of experiments, okay? They cast thousands of number of beams, all right? And they eventually find out that the shear resistance of VC, okay? Shear resistance of VC has some equation, or is a equation of variable of V prime C, compressive strength of concrete, and the depths of the beam. Depths of the beam. So normalize here B, and this is what they have. And now they even find an equation for it, right? And they have a lot of dots, basically. They test it, right? They fail here, fail here, fail there, fail there. A lot of points, right? A lot of points, thousands of points. And they eventually fit a line. They eventually fit a line through it, and they find an equation for it. Okay, and now they say VC essentially is what? Is 2 lambda square root of F prime C and BW, which is the width of the beam, and D. And that is the empirical equation. Okay, now you guys know English better than I do. What does the word empirical mean? Empirical mean? Oh, come on. What does the word empirical mean?
Measured data.
Say it again.
Measured data.
Measured data. Yes, something related to that, right? No shame. You know, first I learned this word empirical. I thought something related to like Game of Thrones, Empire, all that kind of stuff. See? So what does the word empirical mean? Meaning it's based on data, right? Based on what? Experiences. Okay, based on experience. So meaning this equation, ladies and gentlemen, very important, is not theoretically derived. It's not theoretically derived. There is no theoretical model for this equation. It's purely fitted from data. Okay, why this is so important? Because I want you to know that the whole business, design business, heavily depend on experience. Okay, so a lot of applied mathematics doesn't work here. Okay, got to be careful on this. All right, so keep continuing. Now you see this equation here. What is lambda? First of all, have you seen this before? Somewhere, right? Chapter 0 to chapter 3, when we talk about the tensile strength of the concrete, what is the modulus rupture FR equal to? Remember? Long time ago, galaxy far away, there's a Bob saying 7.5 multiplied by what? Lambda, right? Square root of prime C. And lambda equal to what? 1.0 when it's normal weight concrete, isn't it? And lambda equal to what? 0.75 when it's what? Lightweight concrete. It was never before, lambda was not important. Okay, lambda was not important, but now lambda it is very important. Very important. Okay, all right, you get that idea. So now this is the equation. Now what is BW? BW is the minimum width. So when I say minimum width, if I have a T-beam, BW is the width of the web. Is that right? That's easy. For rectangular beam, well, needless to say, it is just the width of the rectangular, right? What if I have a box girder? What is the BW for a box girder? Give you a choice, BF on the top, section height T here, section width T here. Which one? Which one? Think a little bit. Which one? Neither, right? 2T is the right answer. Why is that? Because we have to do the cross. So BW is the narrowest width when I cut through the cross section, right? So in this case, BW equal to what? 2T. Don't forget, there's another T here. Okay, got it? It's always the narrowest length or width across any sections. Okay, and you say, Bob, what if I have a W beam? And my drawing is totally horrible. I understand that. Say if this is T and this is T, all the twos, right? T, it's like my crooked mouse here, right? What is BW? What is BW? 4T. Okay, and what if I have a number like this? Right, just like the birthday cake, right? Birthday cake candles, right? What is my T? What is my T? Sorry, what is my BW? What we say? The narrowest section when I draw the line across the section, right? So if I draw a line, I can find a line that barely cross only this region, right? So BW is what? BW is what? T. Okay, so only in the narrowest, very, very important. Okay, now the other thing, what about D here? So simply D is what? DT or DS? DT or DS? D is so-called effective depth, right? So DT or DS? Yes. Details, folks. Okay, very important. Got it wrong? Got it. Right? So you cannot get it wrong. So when you do the flexure design, you already got the effective depth. So in a sense, whenever we do whenever we do shear, we have done the flexure already. Okay, you have that information carried through. All right, you have to use the same information. Okay, all right, so that's about that. All right, so F prime C, compressive strength of concrete, you know that, right? Not so bad. Okay, so compressive strength. Okay, very straightforward, very straightforward. Now the real problem comes is this, right? What if I don't know DS? What if I don't know DS? For instance, if I don't know the section even, right? Like a jump ahead, right? Like I said, I always do flexure design first, but just in case I want to jump, I can say that DS is approximately equal to 0.h. Okay, that is something you need to know. All right, so that is in the equation of ACI table 22.5.5.1. Okay. And if you flip there, and if you go to Canvas on the file folder, in the file folder, I have uploaded a table, okay? I have uploaded a table. Let me share you the table here. And that, ladies and gentlemen, is a table here, okay? ACI table 22.5.5.1. And I said ACI 318.19, okay? 19, version 19, all right? So what you notice, is the same equation? Oh, not showing, sorry. Look at me, right? Always. Okay, here. What do you see? Do you see the equation? Question? Yeah, sorry, approximately PSI, yeah. When you see a square root of approximately, always PSI, okay? Sorry for that, okay? Let's just put a note here, PSI. Anyway, so when you see this table, do you find the equation I just introduced? Do you see it? Because I don't. I sure didn't. Why? Look at the three equations. The first one is the most similar one, all right? Read it. 2 lambda square root prime C plus, right? There's something there, right? Plus, right? And U divided by 6AG, and U is the axial force applied to the beam. If there's any pretension, there's any tie structure, compression force, and AG is the area of the gross section, entire section. So that is kind of like average compressive stress to the beam. And we don't really have any compressive stress in our class here. So don't have to worry about it. Okay, don't have to worry about it. And that's why if you take this term out, that becomes the equation we have seen so far. Is that right? Okay, now the second equation, so either or. So this means, look at the table, right? This means AV, and I'll tell you in a second, is the amount of reinforcement provided in the shear, okay? Amount of reinforcement provided shear. If AV is greater than or equal to AV mean, of course, AV mean is lower limit of how much reinforcement for shear you need to put in. If this is satisfied, you can pick the top and bottom section, okay? And we are only picking the top section because that was there in ACI 318.14. They added this at ACI 318.19, okay, just as alternative. And truth be told, this fellow here, A lambda, it is more of a hybrid between the empirical equation and the theoretical models. All right, so ACI is evolving, okay, but we don't need to use that. Why is that? Because we found 2 lambda very practical, very safe on the more conservative side of it, so we use 2 lambda. Okay, all right, so only the first equation on the top is what we use. And you see there's another equation here. It says that if AV is smaller than AV mean, use this equation. Now, in our practical design, we will never have AV smaller than AV mean. Okay, why bother? So you might ask, okay, so if you always provide enough reinforcement, why this equation is here? Because in some cases, for example, repair or existing structures, right? For example, the monument of Washington Square, right? And those are done like 100 years, 50 years ago, right? When the code was different. So when the existing condition happened, you might use this to estimate how much strength you have from the concrete. All right, so why am I babbling about all these equations? Because the whole point is that use the first equation. Don't go to the second and third, okay? Don't go to the second for now. All right, later on, if you develop interest, come talk to me and we show you how those were developed and listing the pros and cons. In this class, only the first equation, and forget about axial stress effect, okay? Forget about NU over AG. Clear? All right, okay, I don't want to ask more, questions if you have gone through this in ACI, okay? Take a look at your ACI code and make sure you understand all this and pick the first equation only, okay? All right, 2 lambda. Okay, so quickly coming back. That's about it on this shear design equation. And we're going to use 2 lambda only, okay? 2 lambda only. So here, if we're going to use 2 lambda, which is fine, and lost my canvas again, which is fine. And then I say, look, if I want to use this equation, right, I can start writing the design for it. And here is what I'm going to do. I have VC equal to this fellow here. And then I start write the design equation, which is phi Vn equal to phi Vc plus Vs, and has to be greater than or equal to Vu. So translating to our language, 0.75 multiply bracket inside 2 lambda square root of prime C VWD plus Vs is greater than or equal to Vu. All right, so that's what it is. Okay, so when I keep writing it, I say Vs basically has to be greater than or equal to Vu divided by 0.75 minus 2 lambda square root of prime C VWD. So now I can get my reinforcement. Okay, why is that? Because this is the shear resistance by steel. Okay, but knowing this is not enough. Why it is not enough? Because now, if I look at the free body diagram, okay, if I look at the free body diagram, and I use red color indicating where the shear resistance coming from. VCY is the shear resistance by concrete compressive zone. VA is the diagonal shear resistance, and VD is the dowel resistance, and they all counted. They are all accounted for in VC, right? They're all counted VC. And for steel, where is the reinforcement start to play? The reinforcement will be actually here, isn't it? Remember the reinforcement cages we drew last time? The stirrups will be here. And each of the stirrups will provide the resistance, say T. Okay, So the total shear force, right, for each stirrups. Now, assuming each stirrups will have area of AV. First time you see this word AV, okay? AV is the reinforcement of the stirrups, reinforcement area for the stirrups. Okay, so T for each stirrups resistance got equal to AV multiplied by the yield strength of the stirrups FYT. So FYT is the yield strength of the stirrups. Okay, all right. So FYT is not hard. FYT is the yield strength of the stirrups, right? And for all we know, we have 40 KSI and 60 KSI for the stirrups. The only problem is AV. Now, if you remember, when we draw the stirrups, they're like this, isn't it? Top bar goes here, bottom bars goes here, all right? And when I do the area of the reinforcement for a stirrups, how many legs I have? How many legs I have? Have you ever eaten crab? Did you count the legs? I actually do that. My cousin always steal from me, right? So I gotta count how many legs are there in the crab. So for stirrups, how many legs are there? How many legs? So when I do the cross-section cut, right? I gotta cut here how many legs I have. One leg and what? Two legs, right? Why that is so important? Because say I got a number 3 stirrups. Okay, and what is area for number 3 stirrups? Hard to know, right? Now each leg, number 3 bar, if you look at a table A5 in appendix, right? Not A5, but table A4, I think, in your textbook, right? Each bar in number 3, I have a cross-section area of 0.11 inch squared. So AV equal to what? AV equal to 2 legs, so 0.22 inch squared. Okay. Okay. Why this is so important? Because sometimes I say, you know, I don't like one loop stirrups. I may have this kind of crazy arrangement. That happens in the seismic loading, earthquake. Okay. And now if I have this kind of arrangement, how many legs I have if this is number 3? 4, isn't it? In this situation, 4, isn't it? So that is the difference. Okay. So the cross-section area reinforcement in terms of shear, it depends on the stirrups. Okay, depends on the stirrups. All right, so that is easy. So this tells you that each stirrup will take care of the tension T as AV FYT. Now, for that, I say the total shear resistance provided for the steel should equal to what? Should equal to what? I have T, which is 1 stirrup, isn't it? Right, let me take this red out so you can see better. So T is 1 stirrups, right? How many stirrups I have in this? How many stirrups I have in this drawing? How many? Come on, guys. 1, 2, 3, right? 3, right? So if I were to write it, I say, look, Vs equal to T multiplied by 3. All right? But let me ask you, do you want to go back to count them every time when you design for shear? Do you want to go there every time, draw the drawing, count them before you do the design? Probably not. Don't have time for it. So we need to estimate how many stirrups are there in this cut, isn't it? So how to estimate? How to estimate? Now the diagonal crack, right? We say we call it diagonal, meaning it is what? 45 degrees. Okay, meaning it's 45 degrees. So if I say that this cut right here, fellows, if this cut distance right here is D, most likely I can approximate this length to be another D, because tangent 45 degree equal to 1 and equal to D over D. So triangle, right? Right angle, 45 degree, nice triangle there. Is that right? So if I know the spacing between the stirrups, say, okay, if I design them to be spaced uniformly as spacing S, in this cut, how many number of stirrups I may have here? D divided by what? Divided by what? Yes. That is how do we do the count. Okay, that is how do we do the count. So if this is the case, I say, well, you know what? I can make this general. So this becomes D over S. That is how we estimate shear for the reinforcement. We literally count it for the stirrups, but we do it in terms of calculation. Okay, we do it in terms of calculation, right? T multiplied by D over S. Okay, now D is something we know, effective depth. The critical design parameter here, you notice is what? Plus it is what? Is S. Why is that? Normally, the bar size for stirrups is fixed, either number 3 or number 4. Nothing you can change about, right? You use whatever available to you, right? But critical parameter we can change is what? The spacing, right? Between stirrups. So why I do this? Because I do this expose the parameter S here in this equation. So I can design for it. Okay. All right. So with this, I started thinking, now, if I put this equation in, Vs should be, don't forget, greater than or equal to Vu divided by phi minus 2 lambda square root F prime C BWD. And now, if I put this equation here, that means T is AVFY T D over S has to be greater than or equal to Vu divided by phi minus hoopla prime C BWD, right? And then what I need to get is the spacing S. Spacing S, right? I can manipulate the equation has to be smaller than or equal to V, right? AVFYT multiplied by D divided by VU phi minus 2 lambda square root F prime C BWD. All right. All right. What did I just do? I now got an equation about how we calculate the spacing required for the stirrups, then finish the design. Right? So I go from the ply shear, I know how much concrete can provide, whatever left has to be taken care of by the reinforcement, right? And I get a relationship to be the spacing between the stirrups. So all I have to do is calculate spacing for the stirrups. And that's why when you go to job site, right? You will never hear from the guy say, oh, I need to provide number 3 to number 4 stirrups. No, they will not say that. They will say 2 inch, 4 inch, right? If you don't know, you're out of the game, right? 2 inch, 4 inch, meaning what? The spacing between the stirrups is 2 inch or 4 inch, usually like that. 2 inches is pretty tight. You heard that it's probably going to be in the compressor zone for the pre-stress beam because it needs to have a stress block. Or 4 inches is pretty regular for shear spec. Okay, so that's where all this is coming from. Got it? Okay, all right, good deal. So that is how we do the theoretical calculation. Okay, and of course, the reality is a little bit different. I'll show you in a second, but this is the theory. This is the theory. Okay, so far, everything's been nice and cushy, right? Everything's just rainbow, right? Beautifully arranged. But Bob here is not a regular guy, right? He likes hard stuff, right? He said, you know what? This regular sterile thing is kind of boring. Okay, it is kind of boring. And I say, I use the same free body diagram. And I started thinking, what if I want to do inclined stirrups? That means if I arrange my stirrups like this. Is that even legal? Yes, of course it is legal. I can do whatever I want, right? If I have the money, I will just ask the guys to fabricate like that because that can accommodate some seismic resistance. We'll talk about that later, okay? But if you see this, don't panic. All right, say, oh, this is difficult, right? But you say, now, if I have an inclined angle of alpha for all these, and they have to be the same angle, okay? Yeah, it had to be the same angle. So AVFYT, AVFYT, AVFYT for each of them. And now save you all the trouble. And you can probably find this from the textbook, but for an inclined stirrups, the shear resistance will be AVFYT multiply D over S, same thing as a straight, but multiply a factor that is sine alpha plus a cosine alpha. Okay, so for your knowledge, it's not a big deal. I just need to multiply this factor here for inclined stirrups. Okay, all right, that's it. That's it. I promise you, I will not ask you guys to do this in exam number 2, okay? But you need to know. if you get out of this class, somebody ask you, what if I have to put my stirrup this way to avoid some congestion issues? You said, no problem. We can do that. Just factor something here. Okay, that's all you need to know for this. All right. Okay, so then we are really done with the theoretical stuff. Okay, we're really done with the theoretical stuff. So I want to list all the theoretical equations. Okay, all shear design equations. And mind you that this should go onto your crib sheet. Okay, this should go onto your crib sheet. So at this point, I say, look, Vn, or should I say phi Vn equal to phi Vc plus U, and Vs has to be greater than or equal to Vu, and Vc equal to 2 lambda square root F prime C BWD, Vs equal to AV Fyt multiply D over S, or this is straight stirrups, or Vs inclined, Vs in equal to AV Fyt D over S multiply sine alpha plus cosine alpha. Okay, inclined. Alpha being the angle of the stirrups with respect to the horizontal or flexural reinforcement directions. Okay, flexural reinforcement direction, alpha is the sharp angle. Okay, not the other way around. All right. So this, ladies and gentlemen, conclude everything we need to know for shear. Okay. Conclude everything we need to know for shear in theory. Are we done? Shall I log it out and walk out of the room? I wish. Yes, of course. I wish. But this is only theory. You probably know about this by now. Practical, right? Practical design is quite different from theory. Okay, from theory. So what do we need to know about practical design? Is we actually have to find out how do we design for shear. All right. Now, one thing, if you look at okay, ACI 318, so practical design for shear. If you look at the table 22.5.1.1, we said there's a term called AV mean. Okay, there's a term called AV mean. So what do I mean by that? Why there's a term called AV mean? AV is what? The area for the stirrups for shear, isn't it? Right? And how do we determine AV? We don't determine that. We actually determine spacing. Is that right? Determine spacing. But apparently there are requirements from ACI said you have to put some stirrups in it. Now I understand that, right? I need to have stirrups. But when I have a situation that VC, when I have a situation that VC and phi in front of it is already greater than or equal to VU. What does it mean? What does it mean? It means that the concrete itself can probably carry the shear resistance alone already. Is that right? Situation like this could happen. If the concrete is a giant section, I'm fine. What if I don't need any stirrup by theoretical calculation, right? The theory says, right, I need to do this and find out whatever in a VS. But if phi VC already greater than VU, what's the point? What's the point, right? That's the question. So ACI says, I don't care. You got to put some steel in it. You got to put some steel in it. I cannot have a plain concrete stuff sitting there alone. Just can't. Just can't. Okay, for safety concerns. So it says, at least provide me something. Provide me something. And that something is an equation of 0.75. And write this down, please, folks. F prime C squared, of course, BW and multiply spacing S divided by Fyt and the yield strength of the stirrups. And in addition, ACI said this number, even if you calculate it out, has to be greater than or equal to 50 BWS divided by Fyt. And this, gentlemen, ladies, you can find this in the table, no table, sorry, in the code ACI 9.3.3. Okay. But this does have an exception, okay? Exception is listed in ACI 9.6.3.1, and we will talk about next lecture about exception, okay? But right now, all you need to remember is this fellow here. right? This fellow here. Now, in this equation, I have 0.75, sure. I have square root f prime c, fine. F of yt, fine. Yield strength, and F BW, we talk about it. One thing that I hate to see actually appear here is the design parameter S. Why is that? Because if there's no design parameter S, I don't care about AV min. Is that right? I don't care to throw something, check it, and fine. Is that right? But because the design parameter S was involved in this equation, meaning all my theoretical calculation, theoretical pathway has gone out of the window. Because I have to gauge my theoretical design with my minimum requirement. Is that right? So matter of fact, you see more that ACI dictated requirement dominance in terms of design. So all the theory stuff we said are out of the window. 80% of the time when we do shear design, we do not calculate the space. We just have to use the minimum requirement of space. Okay, so that's sad, but that is actually the real story here. So why I said all the theory, right? 5 minutes gone. Very easy, very simple, but we don't use them. We have a lot of safety concern. Why is that? Because shear is brittle failure. No shear failure ever. Okay, no shear failure ever. If you see a shear failure and the truck is under the rating, okay, then you have trouble. Whoever is responsible, he probably didn't take my class. Okay. All right. And very few out of this university didn't take my concrete class. Okay. If you design for concrete structure, safe, 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 always safe. Okay. It's not like steel. Steel can yield, allow us to run, right? Steel can melt, right? It takes a long time. Concrete, brittle, right? Cannot have brittle failure. All right. So now with that, we start to look at real criteria of how we design for shear. Okay, so just give you a hint. Now, if this is the case, right? If all this, right? So we talk about the theoretical, sorry, the different colors is eye-boggling. So if we talk about all the theoretical development and the practical constraints from ACI asset, okay, how do I do a practical design? How do I do a practical design? Now, which one should I refer to, and what is the sequence I should refer to? So when you do the practical design, what you do actually is to check first VS, whether VS is greater than or equal to VU divided by phi minus VC. Okay, if VS is greater or equal to 0, means you need to have stirrups. Right, by this calculation, if you need to have stirrups for this calculation, then you're fine. Then really out of luck, you say, really you're lucky because now you say I can calculate VS equal to AV FYT. So this is first scenario, AV FYT multiplied by D divided by VU divided by phi minus VC. And once you're in the blue moon, you can actually determine the spacing. What happened? You can actually determine the spacing for the stirrups. Got lucky, right? I can apply my theoretical knowledge, put my professor head down, do the calculation. I'm cool with it, right? But if, okay, you don't have that anymore. Say VU is smaller than phi VC. Okay, what does it mean? Meaning that just the concrete itself can carry the shear resistance. And I say now, for this case, I need to look at in the table, I say AV mean, minimum reinforcement has to equal to 0.75 square root F prime C and BWS divided by FYT. And also this has to be greater than or equal to 50 BWS divided by FYT. Okay. And you think this is done, right? We covered the theory, covered the practical. Sky is blue, grass is green. Go back home, sing Kumbaya, everybody happy? No, unfortunately not. ACI is mean, right? ACI said, this is not enough. All of a sudden, I start forget one thing. Because all this assumption was based on what I just have stirrups in the cut. What if I have a nice section? And just out of luck that I suppose have stirrups here, and I suppose have stirrups, maybe a different color, you see better, okay? I have stirrups here, and I have stairs here. So what if my spacing is greater than the depths? Is this a good thing? It's never a good thing. Why? Because yeah, seems like I put some syrups in it, right? But does it actually work? No, because along the cut, there's no syrups. I, by chance, just hop it, just missed it. So to prevent this from happening, okay, to prevent this happening, ACI says, okay, look, at least, right, provide the spacing between the stirrups required, okay, has to be smaller than half D. Where the half D come from? This is where it come from. Half D meaning at least have one stirrups in the gap. Okay, so that means as max, okay, be careful, the maximum spacing, okay, allowed in the section has to be lesser of, okay, really understand the word lesser, okay? I'm not English major. I know lesser is a lower number of the two, okay? Not a higher number of the two, okay? Lesser of these two, D divided by 2 and 24-inch. So many constraints, okay? And 24-inch. And you find this in the ACI code, 9.7.6.2.2. And just when you think you're done, okay, one more minute, sorry folks. Just when you think you're done, ACI says, wait a minute, I forgot to tell you one thing. What is it? ACI said, look, if my VS, okay, if my VS, meaning my shear resistance by steel is greater than 4 times square root F prime C BWD. What is it for? There was a 2 for concrete, right? That means if the shear has to carry as much as twice as the concrete, then ACI said, oh, no. If you rely all on your steel to take care of your shear, then you better provide me tighter spacing. So ACI said it has to be D divided by 4 or 12 inches, which is half of scenario number 3, right? So this is ACI 9.7.6.2.2. Okay. And just when you feel relief and this lecture is about to be finished, ACI said, don't forget, if, okay, if VU, okay, is greater than or equal to 8 times of square root F prime C BWD, okay, if U is greater than 8 times square root F prime C BWD, redesign your section size. Meaning pick a larger section, in plain words, right? I don't want to be fancy, right? I'm a Missourian, I'm very practical, pick a bigger section, okay? If you need so much shear, right? If you need so much shear, actually, no, VU, sorry. Did I mistake? Yeah. If you need so much shear from the steel, might as well increase your concrete section. Okay. All right. At this point, ACI is done. Okay. So you got to refer to 5 criteria to design a shear, which is horrible, right? And don't worry, Bob will provide a table for you, make everything easier. Okay. We'll see you next lecture. Okay. All right. Thanks. Brock, are you still there? I think we're done.
Yeah, thanks.
Okay, all right. You'll be able to see the recorded video on the YouTube link. I think I've uploaded in the file folder. Just check in there, okay?
Okay, thank you.
Yeah, thanks. See you guys later. Bye.